NMR spectroscopy is the fourth part of the course. So, a formal welcome to nuclear magnetic resonance spectroscopy, or popularly known as NMR spectroscopy, and this in the electromagnetic spectrum corresponds to the radio frequencies in the spectrum. So we first discuss spin and magnetic properties and then briefly look at Stern-Gerlach experiment and then relaxation of nuclear spins and effects like chemical shift and spin-spin coupling. Just like charge is a property, spin is also a property and nuclei show this property. And it is interesting to note that the spin of a nuclei can have values like 1, 2, 3, etc. or even 0, and popular examples are carbon 12 and oxygen 16. And like most of the nuclei show spins like half, three halves, etc. depending upon the number of protons and the neutrons the nuclei have. And the spin of a nucleus is described using quantum numbers I or M. All molecules with a non-zero nuclear spin have a magnetic moment given by nu bar equals gamma times J bar, where gamma is the gyromagnetic ratio and it is constant for a particular nucleus, and J bar is the nuclear spin angular momentum. And after all the experiments and calculations, we find that the angular momentum and the nuclear spin magnetic moment are quantized for a nucleus, that is, they have fixed energies. We now look at the Stern-Gerlach experiment very briefly. So we had silver atoms which has an unpaired 5s electron in its valence shell, and it was passed through the inhomogeneous magnetic field. What we observed was that the beam split into two parts, and we named each part as the spin up state and the spin down state. And with this experiment, Stern and Gerlach concluded that the spin of an electron was quantized. And in a similar way, the spin of a nucleus is also quantized. So nuclear spin angular momentum J bar is given by h bar times I bar, where I bar is a dimensionless spin angular momentum, and the magnitude of spin angular momentum is given by h bar times root of I into I plus 1, where I is the spin quantum number. And we know that nu bar equals gamma times J bar. And for a spin half system, we have Iz equals plus or minus half. These are few examples of nuclei, their spins and their gyromagnetic ratios. And gyromagnetic ratio is given in radians per second per Tesla, and it can also have negative values. Gamma its naught has the dimensions of angular frequency, and that is equal to omega naught, which is called the Lamour frequency. And that is the frequency at which resonance happens. From magnetostatics, we know that the energy of a magnetic moment kept in a magnetic field is given by minus nu bar dot h bar. So from that, we find the Zeeman Hamiltonian or energy term, which is minus h bar omega naught z, where omega naught is the Lamour frequency and Iz is the spin quantum number. For a spin half system, Iz can have plus half or minus half values. Note that the energy corresponding to plus half state is minus h bar omega naught by 2, and the energy corresponding to minus half state is h bar omega naught by 2. We need to note that the splitting of energies happen only in presence of an external magnetic field. The energy difference between the two states is given by h bar omega naught. Now what happens when we increase the magnetic field is that the energy now required for transition is also higher. After the calculations to find the nuclear angular momentum components, we find that the x and y components of angular momentum are not constants, but the z component is a constant, and this tells us that the nucleus in a magnetic field does the spinning motion, and this spinning motion happens around another axis, and this is what we call precession, and the frequency associated with this precession is what we call the Larmor frequency discussed in the last slide. Let's understand relaxation. Consider a case in which the nuclei are in the excited state, and now it has to come back to the lower energy state to absorb energy and show in the NMR spectrum. And this can happen in two ways. Either the excited nucleus could give its energy to the neighboring nuclei or the lattice. And this is what we call the spin lattice relaxation, and the time associated with it is denoted by T1. Or the other case is that it could give its energy to another nucleus in the lower energy state and de-excite itself. And this is what we call the spin-spin relaxation, and the time associated is T2. And we need to note that T2 is always shorter than T1. The idea behind chemical shift is that the electrons that surround the nucleus are in constant motion, spinning and orbital motion. So they create their own magnetic field. Now, following the Lenz's law, this field opposes the applied magnetic field. And so the field experienced by the nucleus is now reduced. So the electrons are said to shield the nucleus. So the actual field experienced by the nucleus is given by this equation. B local equals B naught times 1 minus sigma, where sigma is the shielding constant. Because the local field at the nucleus is thus smaller than B naught, the resonance condition is met even at lower frequency than expected. What happens when there is an electron withdrawing group is that it decreases the electron density at the nucleus, and this deshields the nucleus, so there is a larger chemical shift. Well, chemical shift is defined as the frequency of signal minus the frequency of a standard reference divided by spectrometer frequency times 10 power 6. Now 10 power 6 implies that it is expressed in parts per million or ppm. And the most common standard reference is TMS or tetramethylsilane. So a higher chemical shift implies that it lies in the downfield, implies that the nucleus is deshielded more, implies that the nucleus experiences most of the field. For example, the proton attached to the carbon B is attached to an electron withdrawing group oxygen, unlike the other proton which is attached to carbon A. So the proton attached to carbon B experiences most of the field and thus resonates at a higher frequency, and hence it has a higher chemical shift. Now, if we closely observe at the NMR spectrum of this molecule, we find that the proton A has doublet peaks and proton B has triplet peaks. This is because of spin-spin coupling. The idea behind spin-spin coupling is that protons can be thought of as small magnets since they have magnetic moment, and hence they create magnetic field. And these fields of protons interact with each other. Now let's consider proton A of this molecule. Proton A can interact with two possible orientations of proton B, and hence we see two peaks in the spectrum. Now we consider proton B. You can see all possible orientations of proton A1 and proton A2. So the proton B interacts with all of these possible orientations to produce three peaks in the spectrum, with the center peak with the greatest intensity. And that is because the two of those orientations have the same energy. We observe that the number of lines in a peak is always one more than the number of hydrogens on the neighboring carbon. If you see a doublet in a spectrum, we can conclude that the ratio of heights of the lines in the peak is in the ratio of 1:1. If you see a triplet, then the ratio of heights is 1:2:1. A quadret, 1:3:3:1. And this follows the Pascal's triangle. And you have a beautiful one-line spectrum for fullerene C60, and that is because of its symmetry. But that is not the case with C70 fullerene. To quantify the spin-spin coupling, we introduce the coupling constant J, which is expressed in Hertz. It is actually the difference between two adjacent subpeaks in a split signal. We know chemical shift is dependent on the applied magnetic field, but coupling constant is independent of the applied magnetic field. Let's understand with an example. This example has a coupling constant of 6.1 Hz. So the difference between any two peaks, singlet or doublet, is the coupling constant value 6.1 Hz.